All right, so before we move on, so when I say scaling up, so I'm gonna borrow materials from what Google has done in a couple of years back. So there was a paper named something like large scale accurate prediction modeling with EHR, something like that. So Google announced the very first EHR paper that they worked on in the former Google Brain project team. And what they did is, well, I mean, yeah, I won't go into details. So we'll talk about it today. So before we do that, just quick recap on so far what we've learned so far. So far we've taken on longitudinal EHR. So it could be like outpatients only, or it could be inpatient in ICU setting. But basically, it's a sequence of medical input, medical events over time. It could be diagnosis event, or it could be medication event, or it could be chart events, like measuring heart rates and blood pressure and temperature. So it could be anything that has to do with like temporality, like sequence of medical events. They can all be uh, modeled with RNN. So like this. So if we're talking about if there's first visit with 4 medical events like cough, fever, Tylenol, IV fluid, then this is what you would typically do. Like uh, set a multi-hot vector basically. So a very sparse binary vector. You you embed them into the lower dimensional space, and then put them into the RNN, the hidden layer of the RNN. But this is the first time step, so there's no previous hidden layer. So this is H1, and then you do this again and again and again and again until the end of the sequence, end of the timeline, and then your hidden layer HT becomes your patient representation, and then you do some sort of prediction. It could be mortality prediction, it could be heart failure prediction, it could be hospital readmission prediction, and any prediction basically. But this is the very like straightforward approach to handling longitudinal EHR or time series EHR. These days people use transformers or like one-dimensional convolutional neural networks, or even neural ODEs. But like this is the very basic baseline that you always have to consider when you're developing a new model. Like you first try out the RNN, and if that doesn't work out, then you try to extend the RNN, or maybe you try out different models. But RNNs are very robust to longitudinal EHR data. So it always shows good performance. And I'm not sure if I said this, but it's usually the quality of the data that decides the destiny of your project. It's not the model. It's the quality of the data that you should always focus on. And then if you cannot increase the quality of the data anymore, then you should probably focus on the model architecture. All right, so yeah, this is a recap. So you can use RNN to do this kind of stuff, and then model the patient representation, and then model the outcome. Yeah, this is just 2 demonstrations, like what you can do with heart failure, but I won't go into detail. All right, so what today's focus is the scaling up with CDM, the common data model. So I'm not sure if I've talked about common data model, but it's a hot topic these days in hospitals in Korea. So large hospitals like Seoul National University, Asan Medical Centers, Samsung Medical Centers, and Seoul National University in Bundang. Like they are like top 4 or 5 national level hospitals in Korea. So they would probably, you can assume that they have like millions and millions of patients records that spans over at least 10 or 15 years since they've they've adopted electronic health records, and they're all interested in CDM too. So CDM is the common data model, and I'm sorry if I've already talked about this, but anyway, I'm gonna assume that I haven't. So CDM, CDM was proposed. Common data model was proposed so that hospitals can let's see. So hospitals can potentially transmit data from one place to another, which is heavily restricted actually because of the privacy laws and all that. So the patient records within the hospital are usually never shared externally. It always stays within the hospital. So it is pretty heavily siloed, and different hospitals have different data schemas. So you can assume. Let me just quickly share another my screen again. All right, so stop share screen, Google Chrome. Right. So you are probably familiar with Mimic by now. So Mimic has, I don't know, like 20 different number of tables. And they follow a very specific schema. So everybody here is computer science students, so they know what RDB, relational database, is. And relational database follows a specific schema. So Mimic 3 follows a specific schema where there's like input events, there's diagnosis event, there's date time events, there are prescription event, there's procedure events and all that. But there's another open source CHR that I briefly mentioned today, which is EICU. So it's the same ICU records collected by Philips, which is like electronics company that makes like Razer, like 면도기 and what that kind of stuff, or healthcare products. So Philips has also developed a software for operating or maintaining EHR datasets, and this dataset has a different number of tables with different schemas, right? So there's hospital, there's hospital table, there's diagnosis table, there's medication. Even the names are different. In Mimic, it was prescriptions, but in EICU, it's medications. There are two labs. There's micro labs. So that's already different. And there's like vital sign tables for aperiodic vitals and periodic vitals, which doesn't exist in Mimic counterpart. There's no vital signs here. You have, if you want vital signs like heart rates or temperature, you need to go to chart events and filter them out. But here in EICU, they have a separate table for vital signs. So the schemas are completely different. You can never, like, if you collect a patient record from EICU and try to mix that and try to merge them together with Mimic patient records from Mimic 3, it won't go too well because they follow a very different schemas. So that's why common data model was proposed. So back to the PowerPoints. So that is why common data model was proposed, because every single hospital within the United States or even Korea or anywhere in the world, even though they're electronized, and all the data are stored in electronic format, the format itself is different from hospital to hospital. So there is, like, if you want to do inter-hospital study or inter-site study, or maybe international study for that matter, it's never going to go too well because the formats are too different. So that's why CDM was proposed. So the basic assumption or philosophy is that, well, all the hospitals have different formats, but if they have two sets of data set, one data set in their native format and another data set in a common data model, then maybe we can do inter-hospital studies. So in this scenario is where hospital A tries to send some records to hospital B, but they use different formats, so that's gonna cause problem. In reality, this rarely happens, at least officially. I don't know if doctors share their data with other doctors in other hospital, but at least officially, hospital records usually stays within the hospital. So this kind of never happens. But if it should happen, then why CDM is required is, so hospital A will have their own data set in their own format. They need to convert it to a CDM, a common data model. Here in reality, there are a couple different versions of common data model. There's something called FHIR, which is, in short, is Fast Healthcare Interoperability Resources. There's also OMOP, OMOP. I'm certain maybe some of the people heard about it. So those are the two very famous CDM program or versions. Like, so FHIR is a bit more interested in the management sides. So in Korean, 행정을 위해서 만들어진 거고요. FHIR는 병원의 행정을 위해서. So it's for hospital management. OMOP was developed for research purposes. So it's a bit more friendly towards doing data analysis and doing predictions and that kind of stuff. FHIR is a bit less friendly towards like data analysis. So, but it's the same. I mean, application like using them it applies the same principle is applied. So if hospital A wants to send a certain amount of data to hospital B, then it's gonna cause problems. So what they do is they first take their own data and encode it or map it to FHIR format. So they convert their own data to the FHIR format data, which is the red data now, and then they send it to hospital B. Then the hospital B will they will also have already developed the mapping table between their own data and the FHIR data, so they can decode it, so they can map the FHIR data back to their original data. So that's how two hospitals can communicate, even though they each have different like data formats. So basically, it's kind of like a encoder and decoder. So hospital A encodes data into FHIR format, and then hospital B will decode it back to their own format. So it's kind of like the cryptology, like 암호화, 복호화 type of stuff. All right, so that's the basic philosophy. And so this is kind of side story. Interestingly, I have never seen a hospital in Korea that adopted FHIR CDM. Usually they adopted the OMOP CDM, OMOP, which is interesting because Google has adopted FHIR. All right, so Google uses FHIR to collaborate with multiple partners. So for Google's benefits, so Google will have obviously Google works not only with one hospital, but they work with a lot of different hospitals and a lot of different healthcare partners. They will work with not only just university hospitals, but local hospitals or maybe networks of hospitals. So they have tons of collaborators. So this is exactly kind of the problem that Google will go through. So each hospital will have their own format, and if Google wants to deploy their predictive model to each hospital, then I'm sorry. So, all right. So if Google wants to deploy a predictive model to each hospital, then that means without using the CDM, Google will have to develop n number of predictive models if they work with n number of hospitals, like one predictive model per hospital, because each hospital has different data formats. So they will have different data format. They will have different number of features. They will have different like patient representations. So developing one predictive model for one hospital will not be applicable to other hospitals. So that's going to be very, very cumbersome for Google. So basically it's not scalable. So Google has a imminent like intense interest in adopting a CDM. So they work with different hospitals. So they will receive data sets from each hospital, and then they will convert those data sets to either FHIR or OMOP, some CDM, and then they will develop predictive model for the CDM, and so that they can develop one model that can be deployed to like all the hospitals. So that's the scalable approach compared to developing one predictive model per hospital. So obviously Google adopted FHIR, not OMOP. I don't know why though. I haven't asked that question. But anyway, Google adopted FHIR, so they even open sourced FHIR protobuf. So protobuf is kind of like a data compression algorithm, which is so general that it can be applied to not just like C++. It's like it applies to all the like programming language. You can apply protobufs to Java programs, to C programs, to Python programs. So it's a very general approach, and they developed a protobuf for FHIR as well, because FHIR is a language, of course. So they even open sourced it, and hopefully a lot of people can use it, but I don't think it's flying too well. So FHIR is it's kind of like the same as the RDB tables, relational database tables. FHIR is also it's a format, so they have something called resources. So actually, let me just briefly show you guys. resources. Okay, so this is the official FHIR website. So HL7 is a pretty like big company. I'm sorry, a pretty big company that does a lot of like data related stuff when it comes to EHR. So they defined what FHIR is, and they're trying to sell this. Well, I mean, they're trying to hopefully, I mean, once you've developed something, then you want a lot of users to use it. So they go through like different hospitals or different like healthcare networks to adopt FHIR as their common data model. Anyway, so if you go to FHIR website, there are a lot of resources. So, and for example, if you click patient, then it's the same as the patient table in Mimic or EICU. It has like columns. You can see like, I mean, it's a common data model, so it's not exactly like tables, because tables have columns, but here there are fields, but you can see the fields as the columns. So there's unique identifier for each patient, like the subject IDs. They have the names, they have the cell phone numbers, the gender information, like male or female, birth date. So so basically what you want to do is you go to the Mimic 3, and then you go to the patient table. You go to the patient table, and you want to have a mapping program that maps this table to this resource, which has to be done by a person. It cannot be done without human effort. So it's kind of like very laborsome, but still, if you want to use common data model, that's the kind of thing you have to do. As you've seen, there are a lot of tables. There are like, I don't know, 30, 40 tables. And there are a lot of tables in Mimic 3. So if you want to convert your Mimic 3 to common data model FHIR, then you have to go for each and every single table in Mimic 3, come up with the mapping between a certain column to a certain like field in each different tables. Like there was patient resource, here there's procedures. So procedures resource can be like a lot of stuff in the procedures table here. I mean, there's only 5 rows here, but anyway, so procedures table can be mapped to procedures resource in FHIR, and again, there are a lot of different tables, a lot of different fields, and you have to come up with how you want to map Mimic 3 versions of procedure columns to FHIR procedure field. So inside Google, there's a specific team. There's a particular team that does this all the time. Like they work with like hospital, different partners like provide different types of different format data. So there's a specific team that goes through every single like schema and then try to map it to FHIR, which is very laborsome. Anyway, so once you've done this, once you've populated in FHIR format, then you have 2 sets of data set. You have like original data, and then you have the FHIR version of the data. So once you have the FHIR version of data, then you're good to go. You can collaborate inter-hospital or international. Like you can, I mean, assuming that all the hospitals for example, you want to work with another hospital, as Asan University Hospital trying to work with Samsung Medical Center, then they need to be both prepared to convert their own data set to FHIR data set or OMAP data set, some CDM data set, so that one hospital can develop like data analysis pipeline, like for example, like Python script or R script. They develop their script in-house, then they send that data analysis script to the other party. Like for example, Asan develops their own R script or Python script, and then they send it to Samsung Medical Centers, and then Samsung Medical Center can use the same Python script because they are using the same CDM model. That's kind of the assumption. All right, so that's the end of the FHIR introduction. Going back to the PowerPoint. All right, so I'll skip these 2 examples. So the paper, okay, so the paper that Google is now a couple years ago is titled "Scalable and Accurate Deep Learning for Electronic Health Records." It was submitted to I forgot what this was. NPJ digital medicine. So it's not a very prestigious journal, but still, like, this paper itself got a lot of attention because it was because it was done by Google. So Google is kind of like using their influence in the academic like domain, which is not very ideal. Anyway, so it because it's Google and because it was the first paper from Google using EHR data, it received a lot of, I would say, undeserved attention. But that's just my personal opinion. So what they did is they worked with two hospitals. One is University of California, so UCSF, San Francisco University, California San Francisco Hospital, University of Chicago Medicine, so UCM. Two hospitals. So they received data sets from two separate hospitals, and they converted it to FHIR format, and they developed predictive models for 4 prediction tasks. One is inpatient mortality, another is 30-day readmission, the third is length of stay prediction, the fourth is discharge diagnosis prediction. So I hope that everybody's is familiar with the first 3. The last one is when you're admitted to the hospital, and then when you're discharged. Before you are discharged, you have to pay for the services, and the services are like billed based upon the diagnosis codes, like ICD-9 diagnosis codes. So what they're trying to do is they're trying to predict those ICD-9 diagnosis codes that are given when the patient is discharged. So basically, it's an ICD-9 prediction test. All right. So the way they did it is, I'm not going to go into the technical detail because everybody's already familiar with the RNN. But the key point here is how to pre-process, so how to convert the FHIR data to RNN. And it is very important for Google to not go into detail. So this is FHIR, a single resource. So this is medication order resource, and this is procedure order resource. So this is a timeline. So patient go through the medical events, and each medical event is recorded into a FHIR resource. So like, for example, here, medication order, here, the red line here is, you can see, like, this is the medication order, and procedure order, this is a procedure order. And Google, like, when working with a lot of partners, they don't want to go through every single line and see which line is important and which is not. Like, within the medication order, there were a lot of fields, and you don't want to go into detail, like which fields are important and which fields are not. You just want to dump everything into the RNN, because as a Google, you don't have time and resource to go through every single line of resources to basically do feature engineering. So what they did is they converted everything into FHIR, and then they just dumped everything into FHIR to RNN. And how they dumped it is, as I said, there are a lot of fields in the medication order. There's like code field. So this is medication. So medication named Zosine was ordered. And then the ingredients of Zosine, the ingredient was piperacillin and tazobactam. I don't know what they are, but there are some ingredient. And the code, so the Zosine was you borrow from the coding system called RxNorm. And anyway, there are a lot of effective periods. So the start date of the medication Zosine was like some Unix timestamp. So there are different fields, and what they did is they just converted all the fields into an embedding. It's like some like n-dimensional embedding. So for example, text Zosine was embedded into 2-dimensional space. Coding system RxNorm was converted to like 4-dimensional space. Ingredients were converted to 3-dimensional space. Like, all these like different fields are converted to some latent dimension embedding, because they don't want to care which information is important and which is not. So, and it's the same principle goes to procedure tables and like all the different resources. They did the same thing. So they took all the fields and converted to some number of dimensions, and then they bucketized the timeline. So they use a 1 month bucket, like 1 month here, 1 month here, 1 month here, 1 month here, 1 month here. So within the 1 month bucket, they aggregate all the events that happen within the 1 month bucket. And the way they aggregate it is they just take the embeddings and they just concatenate it horizontally. You can see there's a very, very long horizontal line here. That's because they've concatenated all the embeddings that they mapped from the resource to the latent dimensional space. So first two is like Zosine, the next four is like RX norm, the next three is piperacillin, next three is like tazobactam. So you can assume that a single bucket, a 1 month bucket, will be represented as a very, very horizontally long vector. And then you take the vector and then push them into RNN. And you do that sequentially. So like 1 month bucket, 1 month bucket, 1 month bucket. Every single bucket is represented as a very long horizontally long vector. And then you sequentially push that into the RNN. And that's how you get the patient representation. And they did that for two different hospitals. So one hospital, I think UCSF provided about 9,000, like one training. So training here, test here. So if you sum them up, it's about 90,000 patient records. UCM, Chicago Medicine, provided about 11,000, 12,000. I mean, 120,000 patient records. And then as I said, they trained the same architecture model for 4 different tasks: inpatient mortality, readmission prediction, length of stay, and hospital discharge. But so for the first 3 tasks, the mortality, readmission, and length of stay, there's already a very famous, kind of rather popular algorithm developed by the hospital, like medical experts, which is very heavily feature engineered and human intuition based. So it's a very simple algorithm. Compared to those simple algorithms developed by medical experts or healthcare experts, the RNN does way better for all 3 tasks. So for the last task, the ICD-9 prediction, there was no expert engineered algorithm. So they just compared the first 3 tasks with very well-known expert engineered algorithm, which is like EWS, M Hospital, and some Leo et al. And their model, Google's model, outperforms all the other models in all 3 tasks in 2 different hospitals. So it's very, according to this result, it is a very generalizable approach. I mean, that's what they want. What Google wants to say in this paper is that our method, without a single shred of human expertise or domain knowledge, outperformed algorithms that were heavily human engineered or like feature engineered for 3 different tasks for 2 different hospitals. So like, this is the way to go. This is kind of like Google announcing that this is the future. Right. So yeah, that's the conclusion is that. So without even a single shred of human expertise, like they outperformed like domain knowledge, heavy algorithms that rely heavily upon domain knowledge, and for 2 different hospitals. So like, and it is very scalable. As you can see, you just convert all the things you receive from the hospital to FHIR, and then you just don't care about the individual fields. You just convert the entire FHIR into RNN, and that's it. So you don't need to care about different hospitals. You just develop the same model and just deploy it to all the hospitals with the same model, basically. You don't even care about the hospital specific data formats. So it's a very scalable approach. And yeah, that I'm pretty sure they will try to keep the same pipeline for at least for the foreseeable future. All right, so okay, so we're already at 32. All right, so okay, I'll end. Any question with regard to scaling up? I mean, CDM is a pretty hot topic in, at least in Korea. So if you talk to like hospital data team or IT team or IT engineer team or researchers in hospital, they will always talk about CDMs all the time. So if you're interested, I mean, if you happen to be interested in CDM, you can select that as your course project. Obviously, you could do that. So any question with regard to CDM today? If not, okay, we'll finish the class today. All right, thanks everybody, and have a good rest of the weekend. As I said, I'll try to go through the surveys and come up with like optimal potential team proposal, and then Yeah, I'll see you guys next Tuesday. Bye bye.